Hello, Chem One. How are you doing this evening? I'm excited by this topic. This topic has been around forever. It's kind of like our oxidations. It's been around forever, and it's actually found industrial use that touches our lives every day. So has reductions. And this is actually going to be a little bit of a quick video. We just have one example in this video. We've got one reaction for reduction. And this type of reaction is called a hydrogenation. We're actually going to add hydrogen to an alkene, and that's the hydrogenation. And I put a couple of links on here, as you can see. Ooh, let's use a sparkle pen. And then also where you see this and where you hear it in the news all the time is with our fatty acids and our vegetable oils. And when you hear your trans or cis fats versus your saturated fats, how you get saturated fats is hydrogenation. So there's an article here. I personally haven't read the article, but you may want to check it out. And then you've got something that you can search if you want to look at that. I know several of you are interested in nutrition and several are along those medical and biological lines. So there you go. This is a pretty big area. And then of course your body does reductions. It's just using an enzyme instead of our catalyst. So let's take a look at what the process is. We're literally going to take an alkene right here. And if you notice our product, it's almost like we just erased the double bond. Well, what we did was add hydrogen to it. Now we can take and react hydrogen. This is elemental hydrogen. So this is hydrogen gas in its elemental form. Now you could stir those together for 100 years and not a darn thing is going to happen. What makes this reaction happen is one of our organometallics. We're going to use a palladium catalyst. And we've got a video on organometallics already. And that video kind of goes through why we give a crap about metals. And the next two videos are reduction video and then our Grubbs and Gilman video. We're going to use those metals. So what's awesome, like I said, is this reaction is quite prolific and it wouldn't be possible without that palladium catalyst. Okay, now this is another one of those reactions that we're not actually going to draw the mechanism for. The mechanism in this case is a nice inorganic pathway, but I do want to show a transition. So hydrogen, this is a pretty unique reaction because hydrogen is actually a gas. So you've got to bubble it in. And what typically happens is you put a balloon on your reaction that's full of hydrogen. So you've got an atmosphere of hydrogen. You dissolve your alkene in some sort of solvent, and then you add palladium, which is a solid. So you literally have the reaction happen on the surface of the solid, on the surface of your palladium. So if you could sort of envision, the first thing that happens is your palladium will actually insert into that bond here into our elemental hydrogen. We will do an insertion. So that hydrogen is then coordinated to your palladium. And then you can react your alkene. So let me kind of draw it out here. So if we've got our hydrogen and then we've got our alkene, we can literally kind of picture that you're going to transfer, palladium itself is going to transfer those bonds from hydrogen to your alkene. So again, I'm not going to draw it because remember our organometallics, they work in a cycle. So you have an insertion, we may have another insertion of our alkene onto palladium, and then we can do a reductive elimination or some type of elimination, and palladium is going to spit out that alkane with the hydrogens now attached to that alkane. And so with our process there, the one thing to keep in mind is that this is a solid and this reaction is happening on that surface. So if we want to consider stereochemistry, these will always end up cis because they're literally happening on the surface of a solid. And so your alkene is then adding into those bonds, and those bonds are forming on the same face. So your products will be cis. in this case. In this case, we don't have a stereocenter, and we've got a nice single bond that freely rotates, so you can't tell that it's cis. But the key here is that you have to have palladium, or this reaction isn't going to happen. You could stir hydrogen in an alkene all day long and nothing would happen. But when you add palladium as your catalyst, you're going to do that reduction actually quite quickly. All right, let's show one with stereochemistry just so you can see. This is what I mean. So by the time you add those hydrogens, if you picture this ring, and we kind of picture it in 3D, and maybe it's facing out at us, and we've got that double bond here. So now if your palladium is on the top or on the bottom, and here's your bonds to hydrogen, okay, those new bonds that are forming, they're going to form on the same side of that double bond. So you have no choice. You will end up with the same side with those hydrogens. And now in this case, we have a plane of symmetry. And so it is the same as saying, you know, these are the same thing. But if you were creating stereocenters, remember both of those hydrogens will add cis. So if you've got something with the stereocenter, that might be a nice fun trick question, but they will add cis. And these are actually our reductions. So keep in mind, we're literally going backwards in that oxidation state level because you are taking a bond to carbon and you are now adding bonds to hydrogen, which means you are doing a reduction. You are reducing that alkene and going back to an alkane. So we'll probably see these again. If I don't actually give you the mechanism, I don't ask the mechanism. So I did want you to see that that would happen on the same side. So this we will see in synthesis. We will go backwards from our alkenes. So they might be in some fill in the blanks. They'll be in some questions like that, but they won't be a mechanism question.